Let us start this lecture, and before that we can recall as usual like what we learned in the last lecture and also previously. So, if you look at, we are trying to basically apply the first law of thermodynamics both for the control mass system and control volume system, right. And we have also taken few examples and how to apply that. And if you look at whatever the systems we have discussed is basically non-reacting kind of flows. For example, like like if I consider example of heart of a human being, which is giving the blood supply to your whole body, right. It will be very interesting component to be analyzed by using the first law of thermodynamics. But there, if you look at, there is no chemical reaction is taking place, right. But if I consider a let us say digestion of your food, right, in your digestive tract. So, what is happening? Some reaction will be occurring there, right, metabolism kind of. So, if I want to analyze by using thermodynamics laws, then we will have to consider some of the reactions as well. And some examples like is very important because chemistry is very important in life. Therefore, Jim Eden of the Sheffield University has rightly said, you are a big chemical reaction. Everything you say, all that you do, all that you see, decide or remember or think or feel is nothing but the manifestation of chemical reaction, that is you. So, how beautifully he has really told. And what we will be doing today, we will be basically looking at how to handle the problems wherever there is some chemical reactions will be occurring, because whenever chemical reaction occurs, there will be either some heat will be released or some heat will be what you call absorbed, right. Exothermic reaction or endothermic reaction will be taking place. So, what we will do, we will be basically taking some kind of problem which is related to combustion. So, what do you mean by combustion? Can anybody tell me? Right? Is it something like setting fuel to what you call fire to fuel? So, it is basically, you can think of in layman's term that combustion is a process by which you can just burn the fuel in a controlled manner, right, in a controlled manner. And so, in the combustion, basically there will be several chemical reactions which will be occurring, but they are self-sustained. That means, once it is initiated, you need not to give any further energy, it will be taking care of themselves, right. So, in a more technical way, we can define a combustion is a process during which fuel is reacted with oxidizer while releasing heat and light. Of course, heat is always has to be released, some total of that, but the light you may not see sometime, right. But most of the combustion process you could see, right. What are the examples of combustion process you see? Can anybody tell me? You might have seen like burning of what you call your LPG burner, right, what we use for cooking food. And you might have seen like cigarette burnings, and then diya, like weak flames we have seen, and several other things what you do. And So, for example, if we will consider a burner, let us say, or a combustors, where the chemical reaction is taking place, I mean like into this chamber, the 1 mole of methane is entering. So, also along with the oxygen, right, it will be reacting with each other, and it is giving rise to product of carbon dioxide and water. If you take this as a system boundary, right, you can take this as a system boundary, right, and then it has to be mixed properly. And is it like it will go to directly combustion carbon dioxide and water? Suppose there is a chamber where you are just adding fuel, let us say methane fuel and oxidizer, and it mixed properly. Unless otherwise you give some ignition energy, it will not ignite, it will remain as it is, isn't it? So, if you look at that is in a stable state, but once you give ignition energy, then it will going directly to the what we call to the end product, that is carbon dioxide and water. Keep in mind there might be several reactions which are occurring before really the methane and oxidizer or oxygen getting into the end product carbon dioxide and water, but we are considering only one step kind of reaction. So, and that is very important. You should have of course sufficient amount of ignition energy to have the combustion to take place or in other words for initiation of combustion. So, we will have to see that how to handle, as I told that this, whether we could consider this as a control mass system or control volume. If it is the flow is taking place, right, and then we will consider it as a basically control volume. In this case flow is taking place, I mean like methane is entering, so also oxidizer, and then some reaction is occurring in the what we call in the combustors. So, therefore, we can consider as a control volume system very easily and then for analysis. But however, if some reaction is taking place in a chamber, closed chamber, like you for example, you take some acid and react with some base kind of things, and then what will happen, some kind of product will be coming out there. In chemistry what we do, add some kind of to liquid for reacting, like, and then you will see that there is a some kind of control mass system in it to use it. But in this case we are using a control volume system. So, in this example 1 mole of methane is reacting with 2 moles of the what you call oxygen going to the product of 1 mole of carbon dioxide and 2 moles of water, and giving rise to certain amount of heat release. And if you look at the of course, in this example the moles are balanced, and so also the mass, because 16 gram of methane is reacting with 64 grams of oxygen going to the product of 44 grams of carbon dioxide and 36 grams of water. So, in this case mass is conserved, like kind of things. And if you look at the mole in this example is also balance both the left and right hand side, but in other reaction it need not to, but however mass has to be balance. So, of course, in this process as I told, like the chemical bonds are broken and new bonds are formed, of course, which releases heat, and in some reactions particularly endothermic reactions where the heat has to be absorbed and you need to provide the heat for the reaction to occur. So, mostly air is used as an oxidizer, right, and if you now replace in the chemical reaction, that is instead of oxygen if we will use the air, like in air we are saying that 79 percentage of nitrogen and 21% of oxygen. We are neglecting the other gases which are in very small proportion, negligibly small. So, if you look at the 1 mole of methane is reacting with 2 moles of air is going to the 1 mole of carbon dioxide and 2 moles of water, and of course 7.52 moles of nitrogen. If you look at this is the balance, am I right? If you take this balance, this is the balance equation, and that we call it as a stoichiometric kind of things, and stoichiometric means the minimum amount of oxidizer required for complete combustion of let us say 1 gram of fuel or 1 mole of fuel kind of thing. In this case, the 274.66 kg of air is required for 16 kg of methane. You can call also grams. So, the stoichiometric air fuel ratio will be mass of air divided by mass of F, which is happens to be 17.166. That means, the ratio of air fuel you need to provide, that is 17.166 for complete combustion, right. So, I mean like this we need to have a balance, that is your stoichiometric, but usually what we do, we will have to give excess amount of air for complete combustion in actual case, because that what we have just now saw, that for methane and air we need to give what you call something 17.16, around that ratio has to be maintained, that is the 17.16 is basically air to fuel ratio. But that is theoretical, even if you give in actual case you can't really have complete combustion, therefore, we always give excess amount of air, so that complete combustion can take place. Otherwise, it will be what will happen? It will be causing pollution, because some carbon monoxide and some other unburnt hydrocarbon will be remaining, and also it will be inefficient. It means the entire energy won't be released during these chemical reactions or burning of fuel. So, if I consider 120% of theoretical air, basically it is 1.2 times of theoretical air that we will have to give. And like we will have to define a equivalence ratio, which will tell you like basically whether it is a lean fuel or the rich fuel. That is defined as phi is ratio of fuel air actual divided by fuel air stoichiometric. That means, this is your equivalence ratio kind of things. You can define other way around, that is air fuel stoichiometric divided by air fuel actual, that also some people do define, that is the same thing. And if phi is equal to 1, what is the meaning? If I say the phi is equal to 1, that is equivalence ratio 1, that means you are basically operating on a stoichiometric fuel air ratio, right, or air fuel ratio, whatever you call. And if it is phi is less than 1, means what? That is basically fuel lean, you are giving less amount of fuel as compared to the stoichiometric air what is required, you are giving less. And if phi is greater than 1, that means you are giving more amount of fuel than the whatever the available air is there, kind of things. So, therefore, we call it as a fuel rich, and this will help you to to see with how far you are deviating from the stoichiometric mixture ratio. So, that is why equivalence ratio is being used, and if you keep in mind both the fuel air ratio is a non-dimensional number, so also equivalence ratio, right. And let us take an example how to do this stoichiometric calculation. So, the gasoline, that is we can model it as an octane C8H18 is burned with dry air. It can be moist air also, right, like for example rainy season is on the way. So, at that time you cannot consider the air to be dry, right, because we generally take air from the atmosphere and then use it for combustion purposes. But we are considering dry air, that means it will not be having any water particulates or the steam or the this thing moisture, rather not steam, moisture. And volumetric analysis of product on the dry basis, right, is something carbon dioxide 10.02%, oxygen 5.62% and CO 0.88% and nitrogen of course 83.48% kind of things. And determine air fuel ratio, and we will have to find out percentage of theoretical air use and equivalence ratio, you will have to find it out. So, what we will do, we will basically take this equation, that is X moles of the octane is reacting A moles of air and going to the product. Product is given, like if you look at carbon dioxide is 10.02 and CO is 0.88 and 5.62 is oxygen and 83.48 nitrogen. Of course, the amount of water is not given, so you need to find out. So, basically what we will have to do, we will have to find out this A and then B and then of course the X, that we need to find it out. And keep in mind, this is the one problem where the products are given. In some cases there will be fuel will be given, will be known fuel, let us say CNG gas or some other let us say a producer gas. It will be several constituents. So, you need to find out like this thing. So, we will have to use a procedure which is be easier and also the effective way of doing that. We will be doing basically a mass balance that we have already done, but we will do in a little systematic way. What we will do, we will take the nitrogen. If you look at left hand side, right, what is the nitrogen? Nitrogen 3.76 A is equal to, in the right hand side there is 83.48. Then you can get very easily A, right, A happens to be 22.2. Similarly, we will take C, the carbon, that is in this case left hand side it is 8x is equal to right hand side 10.02 and carbon monoxide, that is 0.08, and you will find out X is equal to 1.36. And now we will consider the hydrogen H, that is 18x is equal to 2B, that is for the water it comes, and then you will get the B is equal to 12.24. And then we can look at O, that is oxygen. On the left hand side is 2A is equal to, for the carbon dioxide 10.02 into 2 and 0.88 for carbon monoxide, and then for oxygen 2 into 5.6, and from water that is B. So, if you look at B, you know X, you know really A. Why I need this? It is just to check whether you have done any mistake or not. Otherwise, there is no need. You can already this all unknown, right? These are all known, these are unknown, this thing. So, it is balanced, but just to cross check that you have done the right. So, you can look at it and it is left hand side is equal to the right hand side. So, therefore, it is the right one. So, this is a systematic way of balancing a equation. Even for the complex one can do that. So, I mean if you look at these all those coefficients we get, then what we can do, we can divide this entire equation, right, by 1.36, then you will get per mole kind of things, right, and that is this expression. Okay. So, from this I can find out air and fuel ratio, that is m A by mass of fuel. So, if you look at the mass of air is basically this portion, right, that is 16.32 into, I can take the molecular weight of oxygen plus 3.76 into 3.76 into, basically it should be 29 plus divided by 12 into 8 plus 18, right, and that will give you 19.65, and the air fuel ratio is basically 19.65 kg of air for kg of fuel. That means, for burning 1 kg of fuel, you need like in this case 19.6 kg of air is being supplied in this example, right. Then we need to find out for 1 kg of this octane, right, how much of air you will have to give for complete combustion in theoretically, right. So, that we will have to find it out, because we are interested to find out equivalence ratio. So, minimum air required for complete combustion of fuel can be obtained by following chemical reaction, that you can do balance, right, and that is 1 mole of the octane is reacting with 12.5 moles of air and giving to the 8 moles of carbon dioxide, 9 moles of water, of course 47 moles of nitrogen kind of things. So, and if you look at the percent of theoretical air, that comes the what you call mass of air, actual divided mass of theoretical, and that will give me the 16 what you call 130% kind of theoretical air will give, right. And the fuel air stoichiometric will be equal to mass of the fuel of the mass of air, that is, if you just put these numbers here, you will get, that is 0.06643, that you will get. And if you look at air fuel ratio, right, what it would be? Air fuel ratio is around something 15.05. This is your case. So, if you look at, this is basically hydrocarbon, right, and so also the methane is an hydrocarbon, but in methane, case of methane, we have seen the air fuel ratio is around 17.16, but in this case it is 15. You keep in mind that for unsaturated hydrocarbon, right, except the methane, most of the things will be air fuel ratio will be roughly 15. You can keep in mind that ballpark number, that ratio which is required, air fuel ratio is required for complete combustion. And then equivalence ratio, this is mass of fuel divided by mass of air actual divided by the mass of air by air to fuel ratio theoretical, right, and that will be giving you 0.766, right. And this is if you look at the equivalence ratio is lean or rich, which is this one? It will be basically lean, it is less than 1, right, and if it is greater than 1, we call it as a rich, fuel rich, okay. And if it is equal to 1, that is basically stoichiometric mixture. So, as I told that in this case the mixture basically is fuel lean. So, we will now look at certain terminologies what we will be using for analyzing this, and most of the things you will be knowing, but I am just trying to make you to recall again, so that you will be comfortable as we go along. So, that is the standard heat of reactions. In this case, what we will consider that 1 kilomole of methane is basically reacting with this what you call burner, right, or a chamber with 2 kilomoles of oxygen, and then it is going to the product of carbon dioxide and water. Keep in mind that it is entering with the 0.1 megapascal of pressure and 25 degree Celsius. It is also leaving at 25 degree Celsius and 0.1 megapascal, right. That is the things what we are saying. That means that whatever the heat is going out of the system will be taken out, then only it will be, otherwise temperature will shoot up because it is an exothermic reaction, heat will be released. So, if that is the case, then we will have to apply the first law of thermodynamics, and this is our what you call the control volume I can take. Okay. This is my system boundary control volume, and if I apply this first law of thermodynamics for a control volume system, so we will have to make some assumption. What are the assumption we are making here? We can say that the change in kinetic energy will be negligibly small, and so also the potential energy, and then what else? And we can assume it to be a steady process, right, and there is no work done. If we will do that, then what will be your first law, I mean what will be the then first law of thermodynamics? What it will be? It will be basically the Q is equal to, that is the heat is going out, nothing but H P, that is dH, right, and which is nothing but H P minus H R. What is H P? Is the enthalpy of the product. These are the product, these are product, right, and these are reactants minus the enthalpy of the reactant, and that is nothing but summation of the moles, the number of moles of each constituents of the product. In this case, I is for the product. In this case, it can be carbon dioxide and water, and enthalpy of the product minus the summation of the moles of the reactant into their corresponding heat of reactants, enthalpy of the reactants. And these, if you look at by definition, is basically delta H 0 naught R at 298, and this is your nothing but your standard heat of reactions, right. So, as I told that HIR is basically enthalpy of reactant per unit mole, and HIP is the enthalpy of product per unit mole, and this delta HR naught, that is at 298, is basically heat of reactions, and this is the things which is you can get basically from a table and kind of things. And that is the standard heat of reaction, because it is being at the ambient temperature and ambient pressure. So, let us consider an example, again the methane. 1 mole of methane is reacting with 2 moles of oxygen going to the 1 mole of carbon dioxide and 2 moles of water. So, in this case, if you look at the N CO2 is 1 and N water, that is the number of moles of water is 2, and oxygen is also 2, and methane is 1 mole. So, delta H naught R is basically the heat of reaction, and that is equal to NCO2 into HFCO2, and this is basically heat of formations of CO2, and the number of moles of course we know, and then heat of formation of water, and these are of course for the methane, heat of formation and oxygen. So, now we need to of course find out this heat of formation of the species at standard state, that is 298.15 Kelvin and of course 101.325 pascals. So, heat of formation is basically energy change during the formation of 1 mole of single compound from the constituent elements, During that, whenever it is being formed, like some heat will be liberated or some heat has to be supplied. For example, if I take CO, C is reacting with the oxygen giving to the carbon dioxide, then a certain amount of heat is being to be released, that is 393,520 kilojoule has to be supplied for that. That means the heat has to be released. So, this HFCO2 is nothing but heat of formation, that is 393,520 kilojoule per kilomole kind of things. And also the heat of formation of carbon is 0 and heat of formation of oxygen 0, because that is at the natural state at the standard temperature and pressure. And this has been considered as that a reference. So, the standard heat of formation can be obtained from the table, and you can use that table. Let me just show you one table for that. And this standard heat of formation is basically can be consisted of two terms. One is what you call standard heat of formations at standard state. This is the like standard heat of formation, and this is your sensible enthalpy. So, this heat of formation at a particular temperature you can get by just taking the data of standard heat of formations, right, and also the take care of sensible enthalpy. For example, like let us say you want to have something heat of formation at let us say 500 Kelvin. So, what you will have to do? You will have to get this data of HFI naught at 298 Kelvin, and then you will have to integrate this CPI values you will take and integrate the sensible energy from 298 to T is let us say, if I say it is something 600 Kelvin, right. So, from that you can get at any temperature you can get the heat of formation. So, these are the heat of formation of important species like is given here. I have given very few examples here, like if you look at, as I told earlier, that the standard state like for oxygen is a standard state at a gaseous state, that is why it is 0. So, also hydrogen, and whereas the water will be minus 242 if it is gaseous state. If it is a liquid state, it is 286. That means, this heat, if you look at the difference, is due to the heat of vaporization, right. And there are several other gases I have given here, carbon monoxide, and then like methane, and there are several of them, and that you need not to remember. This number is very difficult. You will have to use the table for that. And then keep in mind that there is a negative. These are all exothermic reactions here, but let us say nitrogen dioxide is basically positive. It is the endothermic kind of things. That sign indicates the nature of the reaction. So, we will continue that example, like what will they from the table we can get for methane is basically 74,831 kilojoule per kilomole. Similarly, for carbon dioxide and water, and of course, the oxygen at the standard state is 0. Keep in mind that this 0 is considered, this 0 is basically considered a standard state, just as a reference, that to take that as a symbol. So, what we will do, we will basically substitute these values for standard state of heat of formations or heat of formation at standard state, like for carbon dioxide, water and methane and oxygen. If you substitute these values, you will find out heat of reaction is basically 802,405 kilojoule for this reactions. And if you look at, like, we have basically used 1 kilomole of fuel. So, therefore, heat of combustion is nothing but the heat of reaction divided by the moles of fuel, that will give me the what you call heat of combustion, and that happens to the in this case 802,405 kilojoule per kilomole of methane. And if you basically use the multiply this or if you just express this heat of combustion per kg, you will have to take in the denominator you will have to multiply the molecular weight, and then you can get per unit mass kind of things. So, that happens to be 50.15 megajoule per kg of methane. If you, that means if you burnt 1 kg of methane, you will get something 50.15 megajoule of energy, which is very, very large amount, right. Of course, unlike the nuclear reaction, which is much higher, but it is really quite a bit amount of energy. So, if you want to this visualize what is this heat of reactions, you can say that like what you are taking, that is the your reactants here in this, and which is at 298 Kelvin, and the product is at again 298 Kelvin. If you bring this, is nothing but this portion is nothing but your heat of reaction. Keep in mind that this heat, if it will be utilized, then you will reach a temperature that is basically the adiabatic temperature product, which is provided the heat is not going out. We will be discussing how to calculate this temperature, adiabatic temperature kind of things. So, if you look at, we need to use this Hayes law, which is nothing but the first law of thermodynamics for the chemical reaction, and which state that in a chemical reaction the resultant heat is the same irrespective of the number of steps it is being taken during the chemical reactions, right. So, let us that means the net heat of reaction depends only on the initial and the final state. It does not depend what the path is being taken for which might be involve several number of reactions. To give an example, like if you look at like 1 mole of methane is reacting with, let us say 2 moles of oxygen going to the product of carbon dioxide and water, there might be several reaction which will be taking place. Here we are just modeling it as if you when you will work with the actual system, there will be several multi-step chemistry will be taking place, right. And then whatever the heat will be released in the single step, it will be same as that of the, there might be something, let us say 40 reactions are taking place, right, for to a methane combustion, right, with the air. So, then the heat release will be same. So, that is the saying, that is the net heat of reaction depends only on the initial and final state. It does not depend on the path taken by the chemical reactions, kind of thing. So, to illustrate, let us take that an example of water gas shift reaction, and we will have to find out heat of reaction for this. So, if you look at the water shift gas reaction is basically the 1 mole of carbon dioxide is reacting with the 1 mole of hydrogen and going to the product of 1 mole of carbon dioxide and water, and the amount of heat release is basically something 41.16 kilojoule kind of things. But it can really go in the very undergoing several intermediate reaction. That means, several reaction will be taking place in between. Let us say that carbon dioxide is being decomposed into C plus O2, which is basically endothermic reaction in this case, that is 393.51 kilojoules, and this carbon is reacting with oxygen, is going to the carbon monoxide. This is an exothermic reaction, which is 110.59 kilojoule being energy being released, and then hydrogen is reacting with half oxygen and going to the product water. So, if you look at, that is basically this, if you will just add all those things, this will be cancel it out, and this together, this half will be cancelling it out. So, what you will get CO2 plus hydrogen going to the 1 mole of carbon monoxide and 1 mole of water. So, that if you add together, that you are getting 41.16 kilojoule. This is nothing but your what you call, you are applying the first law of thermodynamics, that is the heat whatever the what you call being it is released, it will be basically not dependent on the what you call not on the path, rather it will be dependent on the initial and final state. In this case, basically it is the enthalpy change, right, that is the what we are considering. So, what we will be doing is basically adiabatic flame temperature we will be considering. Now, let us consider that a burner, in case the fuel is reacting with oxygen air and it is giving rise to the product, and let us say that we will take a system here and we are taking the control volume and no heat being going out, that we are considering, right. So, and if you look at what are the assumption we are having same thing, that means change in the kinetic energy is 0 and change in potential energy 0 and no work is being done in this case, and then heat release is 0. So, therefore, it will be first law of thermodynamics gives thing to the heat of product, or the total enthalpy of the product is equal to total enthalpy of reactant, right. Okay. So, that already we have done when we are doing this heat of reaction. In that case, the Q we are considering, but now Q is 0. So, therefore, H P is equal to H R. And if you look at H P is nothing but summation of the moles and then heat of what you call enthalpy of the product, and that is nothing but your moles into, this is your heat of formation, standard heat of formation, right. This is heat of formation at STP, standard temperature and pressure, and this is your sensible enthalpy. Right. Of course, with n coming into picture, otherwise it will be specific sensible enthalpy. And HR will be similar things, I mean only the what you call, it is the reactants, it is meant for the reactants. So, what you will do, you will just use that thing and then find out what will be adiabatic temperature. So, if you consider this, that by definition this NIP HFIP, I mean minus NIR HF for the reactant, and this is nothing but your heat of reactions, right, you can get very easily. And then other things, what we will say that this sensible enthalpy, that is the terms which we have seen, that when we are considering the balance of enthalpy of the product and is equal to the enthalpy of reactants. And then this is basically from the some temperature, standard temperature, that is equal to 298 Kelvin, you can say T is equal to anything, let us say if it is 600 Kelvin kind of thing, that is you can take if it is the inlet condition is 600. Otherwise, what will say, this will be your 298 Kelvin also, right. But whereas the product will be, this is 298 Kelvin and this is the adiabatic temperature. That means, this is a general equation which can be applied for anything, right. Suppose the reactant is coming at 298 Kelvin, what will happen to this term? This term will be what? 0, because it is integrated 298 to 298. So, it will be 0, right. And whereas the product, always it has to go to certain temperature, because no heat being going out of the system. So, therefore, it has to go to the adiabatic temperature. So, what is saying that? That means the reactant at the standard temperature, it is going to the product at the standard temperature, that is nothing but your heat release, right. This is the heat of reaction, and this heat of reaction, right, will be basically what you call utilize here to raise this temperature, right, this heat of reaction whatever it is raising, and then the product you are getting, that is adiabatic temperature. And keep in mind that this is a very important point, that Cp, whatever we are using here in the particularly product, will be having very high temperature. So, therefore, this is a function of temperature Cp, which is constituted of A plus B T and C plus C T square plus D T Q, and these A, B, C, D are constant, and these constants will be varying for each species. Each species means for carbon dioxide it may be different, oxygen it will be different, and water it will be different. So, that has to be taken care. So, it is a quite difficult to integrate this term, this term to integrate is quite difficult. So, therefore, what we will be doing in our calculation, we will be using some average properties of the Cp and then trying to calculate, but in actual case generally numerically it has to be integrated. So, we will take an example, they estimate the adiabatic flame temperature of the pentane, like that is C5S12 with 25 excess of air, and both C5S12 and air enter the burner at 25 degrees Celsius. So, same thing condition will be having, that control volume system will be taking, and then Hp is equal to Hr, right, and you can do this balance, and if you I can find out this, I can write down Hp is equal to 5 into HFCO2 plus 6 HF water and 2 HF oxygen and 37 points of the nitrogen, right. And this is your what you call heat of formation, these are basically heat of formation you can get, these terms are heat of formation at standard state like STP, and whereas these are your sensible enthalpy, what we are assuming in this case it is integrated T adiabatic to minus T 298 Kelvin, and we are saying that the Cp values are not function of temperature, in this case we are assuming, right. Therefore, we are taking out and doing that. And of course, Hr will be with the heat of formation, you can say all those for the pentane and oxygen and nitrogen, right. And there is no sensible enthalpy here, because it is at the ambient temperature to start with, right. So, therefore, there is no sensible enthalpy in this case. So, we know that H P is equal to H R, and we will just do that, and when we will do this, we will find out this is nothing but H R is equal to this portion, right, and this is nothing but your what you call, and which is equal to the sensible enthalpy, and this H R naught is 3271.71 kilojoules, right. If you just do these values over here and put these average values of CPs corresponding certain temperatures, right, these values are average values. For example, these are these average values of the CO2, right, this portion. We have taken average value that will be given to you, or it will, you will have to find it out, and then you will calculate T adiabatic is 1852.3 Kelvin. Keep in mind that if you are not taking proper values of Cp, then you won't get the proper adiabatic temperature. You will be, because that will be dictating the what temperature you will be getting in your calculation, right. And keep in mind that here we have used the control what you call volume system, right. Now, if I say that control mass system, how to calculate adiabatic temperature, that I am giving you as an assignment. You do that. What you will have to do there, basically you will have to say not the internal energy U of the product is equal to internal energy of the reactant. That is all you will get, okay. And from that you will have to calculate what will be adiabatic temperature. Let me ask you another question, which will be higher for the same system, for the, let us say, if I consider this pentane air, right, whether the adiabatic temperature by using the control mass system will give me higher adiabatic temperature, or it will be lower as compared to the control volume system. That I will leave with you, and then we will then let us look at that what will happen to equivalence what you call ratios. If you look at that, it will be having peak temperature here at 1, at equivalence 1, this will be having peak temperature something 2250 kind of things, and both the lean side, this is your lean mixture side, lean fuel, fuel lean side, right. This is it drops down, and of course on the reach side it drops down at a lower slope. This is fuel reach side, equivalence ratio greater than 1. And as you increase this temperature, inlet temperature to 600 Kelvin, the temperature also increases, having similar features. So, if you look at, like, instead of methane air, if we are using methane oxygen, if you look at, there is an increase in temperature kind of things for the same pressure and same stoichiometric mixtures kind of things, right. There is a increase in temperature. Now, if you look at like if I take hydrogen oxygen, it is a very higher temperature, right, as compared to the hydrogen air, right, because the nitrogen is a diluent. So, therefore, it is absorbing large amount of heat, and here the nitrogen not there, therefore, this is being higher. So, therefore, the adiabatic temperature will be not only depending on the fuel air ratio, it will be depending on the inlet temperature, it will be depending on the also the whether it is air or oxygen or any other things, that way you will be. So, basically we will stop over. We have learned how to apply the first law of thermodynamics to take care of reacting systems, and we have also seen how to calculate adiabatic temperature, and it will be also adiabatic temperature will be dependent on the pressure. If you look at the one like pressure is 0.1 megapascals, and when it will increase for methane air to 2, then the temperature has increased from 2200 to 2270 for the same stoichiometric mixture. So, it is also dependent on the pressure, right. So, I will stop over here, and we will in the next lecture discuss about basically the second law of thermodynamics. Thank you.